Welcome back to linear algebra. In this video, we're going to be looking at the eigenvalue problem. The eigenvalue problem is arguably the most important aspect of linear algebra. The reason that linear algebra is so important to so many people in so many different fields of study is that the idea of a vector space is so generalizable, and there are so many different things that we can construe as vectors. The reason that it's useful to construe things as vectors is because of the eigenvalue problem. So with that in mind, let me get my head out of the way and let's jump into it. A little bit slower than that. We need to start with a square matrix, an n by n matrix that we're calling A. Our goal is to find a vector in Rn and a scalar, which traditionally we represent using the symbol lambda. And our goal is to find the vector and scalar so that when we multiply the matrix A times X, we get lambda times X. This is called the eigenvalue problem. We call the values of lambda for which this actually works the eigenvalues of A, and the vector X is a corresponding eigenvector. Right. The prefix eigen is a German word or a German root that translates roughly as one's own. What we are trying to say, or what the German mathematicians who originally studied this problem were trying to say, is that the eigenvalues are the property of the matrix. Very essentially, the values of the eigenvalues are an essential property of a matrix. And the character of the vectors, of the eigenvectors, is an essential property of the eigenvalues. And again, most values for lambda are not solvable in this sense. For most values of lambda, there is no way to get this result. Sometimes, especially in disciplines other than linear algebra, you will see the eigenvalue problem also referred to as the invariant problem. The property of the eigenvalue problem, the property of that equation that's at the top of the screen now, is that when you apply the matrix transformation A to this particular vector, it does not change the direction. So if we have an eigenvector and we multiply that eigenvector times matrix A, the scale of the vector will change. It will become larger or smaller, and eigenvalues can be whole numbers, integers, fractions, irrational numbers, the whole gamut. But we'll change the scale, but not change the direction. And that property is a useful way of analyzing the solution space of vector equations. It's important to notice that the zero vector is always a solution to the eigenvalue problem. No matter what value you put in for lambda, if you use x equals the zero vector, it always satisfies. We've mentioned before, the zero vector very often is referred to as a trivial solution. It works, it's not useful, and it gets in the way of actually analyzing the thing that is useful. So x equals 0, we've determined, or we've decided, I guess I should say, this can never be an eigenvalue for, or this can never be an eigenvector for any matrix. The zero vector is never an eigenvector. It cannot be used to identify corresponding eigenvalues. It always works, and there's nothing special about that. So we throw it away, we ignore that case. Right. So now that we have an idea that we're working on, we have to figure out a way to actually get there. It turns out that the eigenvalues themselves are easier to come by. If I come back to the eigenvalue problem, ax equals lambda x, I can subtract lambda x from both sides of this equation. I can notice that if I multiply by the identity matrix in a very careful spot, the identity matrix is defined specifically so that it doesn't change anything. And when you're multiplying matrices, and vectors are a special case of matrices, you're multiplying in a scalar, the commutative and associative properties tell us it doesn't matter where we put that scalar. And finally, the distributive property of matrix multiplication tells me that I can factor the x out of this mess that I now have on the left-hand side. And I get this equation. And this is where we can start to use some of the properties that we've developed throughout the course. In the huge list of equivalencies, the matrix equation Bx equals 0 one of the entries in that huge list of equivalencies is that any matrix B times X is equal to the 0 vector, has non-trivial solutions if and only if all the other stuff is true. Of all the other stuff, the most useful one for us here is the one about the determinant. Determinant of B is equal to 0. So in our particular case, A minus lambda I times X is equal to the 0 vector. We know that X equals 0 is always a solution here, but that's not interesting. We want to have non-trivial solutions, and our theorem tells us that we will have non-trivial solutions if this matrix, it's kind of an ugly way of writing a matrix, but it is a matrix. If the determinant of that matrix is equal to 0. We call this the characteristic equation for matrix A, or sometimes the left-hand side of this is referred to as the characteristic polynomial. If we can determine the values for lambda where this equation is true, we will have identified the eigenvalues of the matrix. Once we have the eigenvalues, at least in theory, we should be able to find the eigenvectors. All right. So let's consider a 2x2 matrix to start with. 3, 0, 8, negative 1. Excuse me. This is a 2x2 matrix. We're asked to find the eigenvalues. So we're going to look at the characteristic equation. We're going to look at the equation A minus lambda times I. A in this case is 3, 0, 8, negative 1. And because we're dealing with a 2x2 matrix A, we want the 2x2 identity matrix 1, 0, 0, 1. Multiplying that matrix by lambda gives us lambda 0, 0, lambda. And then subtracting, we end up with a rather ugly looking matrix. 3 minus lambda, 0, 8, negative 1 minus lambda. Now we have the matrix that we want to work with, and the characteristic equation simply asks us to take the determinant of this matrix and set it equal to 0. So the determinant of 3 minus lambda, 0, 8, negative 1 minus lambda. In a 2 by 2 matrix, we multiply the main diagonal entries. So that'll be 3 minus lambda times negative 1 minus lambda. We multiply the off diagonal entries. That'll be 8 times 0, and we subtract. I could multiply that out, but it turns out it's very convenient for us that it's already factored, because the eigenvalue problem asks us to set this equal to 0. And so, using the zero product rule, since we have two things multiplied together equal to 0, that means that either 3 minus lambda is equal to 0, or negative 1 minus lambda is equal to 0. 3 minus lambda is equal to 0, that means that lambda is 3. Negative 1 minus lambda is equal to 0, that means that lambda is negative 1. There are the two eigenvalues for this particular matrix. Let's look at a somewhat more challenging case of a 3 by 3 matrix. Let's find the eigenvalues of matrix A, which is equal to 0, 1, 0, 0, 0, 1, 4, negative 17, 8. Once again, we start off. The characteristic equation asks us to look at the matrix A minus lambda I. And since A is a 3 by 3 matrix, that means we want the 3 by 3 identity matrix. And working through that arithmetic, we get the object matrix, negative lambda 1, 0, 0, negative lambda 1, 4, negative 17, 8 minus lambda. And to find the determinant of this 3 by 3 matrix, we can use the method of cofactor expansion. Either across the first row or the first column seems to make sense. The first row will be a little bit easier because we can deal with 1 instead of 4. So we'll have negative lambda times the determinant of the 2 by 2 submatrix when we get rid of first row and first column. Minus 1 times the determinant of the 2 by 2 matrix when we get rid of first row and second column. Plus 0 times the 2 by 2 matrix when we get rid of the first row and third column. I don't quite have enough room to put that in, but that's actually okay in this case because it's multiplied times 0 and it's going to be 0. All right, so negative lambda times, it'll be negative lambda times 8 minus lambda minus 1 times negative 17. Then it'll be minus 1 times 0 times 8 minus lambda minus 1 times 4, and then plus 0. Couple of more zeros happening here. Just cleaning up a little bit. Unfortunately, we do have multiple terms. We don't have the factored case we did last time, so we don't get to take that shortcut. But we can still continue from here, multiplying everything through. And then set that equal to 0. So here we have a polynomial equation with a third degree polynomial to work with. Unfortunately, there are no signs of anything that's going to help us simplify this process any. When it comes to a third degree polynomial, my first step is generally to look and say, well, is it a perfect cube? If it's not, my second step is to ask, can it be factored by grouping? It cannot. And once you rule out those possibilities, the only thing you're left with is the rational roots test. Since the lead coefficient is, well, negative, but 1, that means that if there is an integer 0 to this polynomial, if there's an integer solution to this equation, 4 must be divisible by whatever that number is. Otherwise, when you multiply it out, you'll end up with a complete mess instead of a nice solution. So we can just check. 1, -1, 2, -2, 4, and -4. Plugging those in fairly quickly. 4 cubed is 64. 4 squared is 16. 8 times 16 is 128. 17 times 4 is 68. So we have negative 64 plus 128, which is positive 64. Minus 68 is negative 4, plus 4 is 0. So trying all of those numbers, saving time by knowing which one is going to actually work before I would talk through all of them. But in preparation, I did walk through and just plug in not x, lambda equals 1, lambda equals -1, lambda equals 2, lambda equals -2, lambda equals 4, and lambda equals -4, looking for something that would work and hoping that at least one of them would. Since I have that lambda equals 4 works, I'll work through the polynomial long division. And so I see that this polynomial is going to factor into lambda minus 4 times negative lambda squared plus 4 lambda minus 1, giving me my lambda minus 4 equals 0, or lambda equals 4, and my negative lambda squared plus 4 lambda minus 1, which I don't see how to factor, but I can always use the quadratic formula once I'm down to a second degree polynomial. Lambda equals negative of b, which is 4, plus or minus the square root of b, which is 4 squared, that's 16, minus 4 times a, which is negative 1, times c, which is negative 1, so that's minus 4, all over 2 times a, which is negative 1. Notice that we can reduce this square root and then divide term by term. Negative 2 divided by negative 2 is negative 1, but we're dealing with plus or minus anyway, so that doesn't change anything. I get lambda equals 4, lambda equals 2 plus the square root of 3, and lambda equals 2 minus the square root of 3 as the 3 eigenvalues for this particular matrix. Sorry about that. Before we wrap up here, 2 quick theorems on properties of eigenvalues. I guess the first one is a property of the characteristic equation, but that's a property of eigenvalues itself. For an n by n matrix A, the characteristic equation forms an nth degree polynomial whose lead term is negative lambda to the nth power. And while I don't quite have a proof for you on that, I can point to the last example as a case where that showed up. And there is a problem in the suggested exercises that asks you to explore this for yourself. But that theorem leads to a very important corollary that I do want to talk about. An n by n matrix A has at most n distinct eigenvalues. Using the theorem that I just talked about, that I said that you're going to be proving in the homework exercises, the characteristic equation is an nth degree polynomial. The solutions of that polynomial are the eigenvalues of the matrix, and the fundamental theorem of algebra tells us that an nth degree polynomial has n roots if you count the multiplicity. So if there is an x minus 3 squared factor in the polynomial, that is 2 roots of x equals 3. Counting that multiplicity gives you n roots. So because there are exactly n roots, some of them are repeated. That means that there are less than or equal to n distinct roots. Another theorem that I want to talk about, I should label this as theorem. The eigenvalues of a triangular matrix are the entries on its main diagonal. The proof of this relies on a fact that we talked about, why we cared about triangular matrices in the first place. That fact is that the determinant of a triangular matrix is the product of the entries on its main diagonal. The first time we talked about triangular matrices, it was when you are trying to find a determinant, if you have this case, it makes it really easy on you. The next thing I want to claim is that if matrix A is triangular, then matrix A minus lambda I is also triangular. And that should make sense if you think about it for a few minutes. The identity matrix I has non-zero entries only on the main diagonal and zeros everywhere else. So when you multiply lambda times I, it still has its non-zero entries, in this case lambda, on the main diagonal and zeros everywhere else. So when you subtract A minus lambda I, the entries on the main diagonal will change, but all of the other entries will stay the same. If they were 0, they stay 0. So whichever side is triangular and has all the zeros, all stay zeros. The last thing that I want to claim is that whatever else is happening in the matrix, the entries on the main diagonal of A minus lambda I are, I'll call them A1, A2 through to AN, the entries on the main diagonal of A itself, each one subtract lambda. And again, the other entries are the same as they were in A in the first place. And then because the determinant of a triangular matrix is the product of the entry on the main diagonals, the determinant of this matrix is A1 minus lambda times A2 minus lambda times until you get to AN minus lambda. And setting that equal to 0, the solutions are going to be lambda equals A1, lambda equals A2, through to lambda equals AN using the zero product rule. With that, I'm going to wrap up my discussion on eigenvalues here. And in the next video, we'll pick up and start talking a little bit about the corresponding eigenvectors.